Okay, in this video we are going to review applications of integration, which if you're in AP Calculus is all of Unit 8. It's like 10 to 15% of the Calc AB exam. It's between 6 and 9% of the BC exam. Shows up in multiple choice, free response. I don't know. If you're in college calculus, it's like the end of Calc 1 and Calc 2 is kind of where I think this would fall. So let's take a look. First section is average value. So what does average value look like? Average value is the integral from a to b of f of x dx divided by b minus a. You will also see it written as 1 over b minus a times the integral from a to b of f of x dx. And in fact, this is pretty much exclusively how you will see it typed on the AP exam because it is more space efficient. And the way that I always remember this and tell my students to think about it is that what we are doing is the integral over the interval. So you're doing the integral from a to b over the interval from a to b, which is b minus a. All right, so now what I'm going to do is show you a couple of problems from the exam and what they look like when they're asking this question. So, for example, from 0 to 20, the average temperature of water in the tub is, there you can see it typed out, 1 over 20, 0 to 20. Use a left Riemann sum with 4 subintervals. So this is really common. You will be asked to approximate average value. And then does it over or underestimate, blah, blah, blah. So there's more information. This is a free response question. But key things here for us, we want to approximate from 1 to 20, which means that we'd want to use an approximately equal to sign. And then one thing that I have noticed with my students over the years, when you're approximating average value, what you definitely don't want to do is forget that 1 over 20, the 1 over b minus a. People forget it all the time. And then you get an answer that doesn't make any sense, right? You'll like have a table of values, the biggest value is like 15, and then when you go to approximate the average value, your average value would be like 240. The reason you're getting that is that you forgot to divide, so don't forget that. That needs to be there. All right, what else might this look like? Well, particle moves along the x-axis, the velocity of the particle at time t is given by v of t, acceleration is given by a of t, so a lot of these are multiple choice questions that I just didn't put the multiple choice options. Some of them I'm going to do as we go along, others I'm just going to set up, and some I'm just going to talk about. But most of these are from like old AP exams, or just like, questions that are very much like AP. So which of the following gives the average velocity of the particle from 0 to 8? Average velocity. So my recommendation is when you see average velocity or average temperature or average height, whatever, in your mind, you should try to think of it as the average value of the velocity function. So like between average and velocity, put value of the, and then velocity function. That'll help you to figure it out. So like in this case, it would be 1 over 8 minus 0, the integral from 0 to 8 of v of t dt. And let's take a look at another one. So just so you can get an idea that like this comes up in the same way every time. This is a review. I have lots of videos where I do a lot of problems. So if you want problems, just search my channel for, average value or whatever topic you see here that you want to see in more depth. All right, so the height of an object is given by h of t. What is the average height? So again, you're being asked for average height. So what I think you should do is you should replace that with average value of the height function, right? We have a function that's giving height. It's h of t. We want the average value of that function. If you do that in your head, it makes it just a little bit easier to think of these things. So this is going to be the integral from 0 to t, h of t dt over 2 minus 0. All right, so that is average value. That's section 8.1. We're going to do all of them. So let's keep going. 8.2. We want to be able to connect position, velocity, and acceleration using integrals. There's also position, velocity, acceleration using derivatives, but that would be in some other unit that I don't know offhand. So the two super relevant things here would be that displacement is just the integral velocity. So if you do the integral velocity from A to B, you're getting the displacement. The other thing is distance. So distance versus displacement is a really big deal. Distance is the integral of the absolute value of the velocity from A to B. And if you remember, the absolute value of velocity is just the speed. So you're just integrating the speed. That's like what you learn in like 7th grade or whatever when you do distance equals rate times time. Like the rate there is really the speed. So distance involves the absolute value. Distance is a pain in the neck to calculate by hand. Displacement is just fundamental theorem, so it's much easier to calculate by hand. A lot of times these are on the calculator section though, and then it doesn't really matter. All right, so let's take a look at what these look like. Write but do not evaluate. That is the greatest thing you can see on any AP exam. An integral expression that gives the total distance traveled by the particle. So total distance is going to involve absolute value. And also on FRQs, you often have to approximate the value instead of actually find it. Here we just had to set it up, probably because it'd be super annoying to actually find. And then let's take a look at another question. Particle moves along the x-axis. The velocity is given by 6t minus t squared. What is the total distance traveled? Okay, so when we're dealing with total distance, you have to be careful because total distance involves the absolute value of velocity. So one of the things you want to do is watch out for zeros of the velocity on the interval. So this problem that I found isn't a good example of this because the zeros are 0 and 6. But although maybe the velocity is actually negative there, I didn't actually try to do this problem. I was just like, oh man, the zeros aren't there. So you also want to watch out for the sign of the velocity. And if I think about it, it opens down. No, okay. So watch out for the sign of velocity. So what I'm going to do here is just make up a sign chart for velocity that would illustrate what I'm trying to talk about. So say our sign chart, we have zeros of our velocity are 0, 2, 4, and 5. Between 0 and 2, you're negative. 2 and 4, you're positive. And then 4 and 5, you're negative again. All right, so to find the total distance traveled, we want to do the integral of the absolute value of velocity from 0 to 5. Now, this is a little more complicated because, I don't know if let me just pause this. All right, between 0 and 2, if I do the definite integral from 0 to 2, I'm going to get a negative answer, right? Because velocity is negative, so displacement is negative. I want to do the integral of the absolute value of velocity. That's hard to do kind of with this chart. So instead, because I know the definite integral is negative, I'm just going to take the negative of it, right? The negative of negative 5 is the absolute value of negative 5. So I'm doing the negative of the integral from 0 to 2. And then plus, because you're positive from 2 to 4, you just add it. You're negative again from 4 to 5, so we're going to subtract that definite integral. Just watch out for the signs of velocities and make sure there aren't zeros you weren't expecting on the interval. That's going to get you through there. All right, let's take a look at another one. So over the time interval from 0 to 5, particle moves along the x-axis. The graph of the particle's velocity is shown above or to the side. Over the interval from 0 to 5, the particle's displacement is 3, and the particle travels a total distance of 13. What is the value of the integral from 2 to 4 of v of t dt? So this, I'm not going to actually solve this, but to do this, you would make that first region A, the second one B, and then the third one C, and then set up kind of a system and solve it. So the key thing here is that displacement doesn't really show up all that often. Like the actual question, what is the displacement? Total distance is asked about way more often. The concept shows up. So like here, we're being told something about displacement. I would say the concept shows up all the time. For example, this is like the one example I could find on a free response where they ask literally for displacement. What is the displacement of the snail? I mean, obviously there you're doing displacement. The concept of displacement shows up a ton, but in a slightly different way. So, and actually it's in the next section. So that's position, velocity, acceleration, I don't know, displacement, integrate velocity, distance, integrate speed. There you go. Let's take a look at the next section where I think displacement comes up a lot, if you think of it as displacement. So 8.3 is accumulation functions and definite integrals. All right, so what does this involve? This mostly involves rearranging the fundamental theorem. So the fundamental theorem is that the integral from a to b of f prime of x dx is f of b minus f of a. Well, that's an equation, and you can rearrange it to solve for f of b, and you can rearrange it to solve for f of a. So I'm going to do both of those. So f of b is going to be f of a plus the integral from a to b of f prime of x dx. So it's like where you started plus the displacement, right? The integral from a to b of f prime of x dx is the displacement of f of x. So where you start plus the displacement, or if you want to figure out where you started, you're where you ended minus the displacement. So this comes up all the time. This is how displacement really, in my mind, shows up on the exam. But but let's take a look at the typical types of problems, I guess. So this is so long. Tank contains 50 liters of oil at T equals 4. Oil is pumped in, rate of R of T. R of T is liters per hour. T is measured in hours. And then there are values in a table and whatever. The question is, what is the approximation of number of liters of oil in the tank at T equals 15 hours? So let's just highlight some of that stuff. There's 50 liters at T equals 4. R of T is the rate of change of oil in liters per hour. And we are looking for oil in the tank at time T equals 15 hours. We're looking for how much you end up with. So if you're looking for how much you end up with, you want to know how much you started plus the displacement. So that's going to be 50 plus the displacement is the integral from 4 to 15 of R of T dt. That's all it is. Let's take a look at another problem. Water is pumped into a tank at a rate of, it's like basically the same problem. R of T equals blah in gallons per minute. T is a number of minutes. Since you returned, you actually do need to like really read the problems. Like I'm glossing over it because I'm just doing a review video. Make sure you actually read and understand the problems. And if you want to read and understand these, just pause the video. If the tank contained 800 gallons when the pump was turned on, so that's what you started with, how much water is in the tank after 20 minutes? So we want what we started with plus the displacement. So whether it's pumped in or out, we're going to do the amount we start with plus the displacement. And if the rate is negative, we'll end up with less than we started with. If the rate is positive, we'll end up with more than we started with. But we're just going to do what we started with plus the displacement. What's relevant here? R of T is the rate of change. 800 is what we started with, and we want to know after 20 minutes. So we're going to do what we started with plus the integral from 0 to 20. So notice in the previous one, we went from 4 to 15 because the amount we started with, or that we knew to begin with, was T equals 4. This time we know like just when we started, so that's 0 to 20. A really interesting thing is both of these are multiple choice questions from the same year of the exam. So this is a concept that they hit a lot. You really have to understand that you can rearrange the fundamental theorem. I mean, it's the fundamental theorem, so it makes sense that it's that important, but like it's going to show up. You can't avoid it. All right, so a couple of things that I think of when I think of this. You often have to approximate these with either a left, right, midpoint, or trapezoidal sum. The first question there was asking you to approximate, for example, using a right Riemann sum. And then the other thing is you're often going to be using this concept to find position from velocity in a starting point. That's like the most common way I think that they use it, despite the fact that maybe the most common way is to figure out how much of some fluid is left after some amount of time. I don't know, but I think of it as find the position you ended up at or find the position you started at using this. Now, another thing that you can do, if you get lost while reading these problems, what you got to do is really focus in on the units, right? Like in the first problem there, it's liters per hour. In the second problem, it's gallons per minute, right? So those are derivatives. Those are rates of change. There's something per something. So if you know the units, you can think about what the integral will give you. So for the second one, we had gallons. No, I don't even know. I just made that one up. That's not even in here. We just have gallons per hour. If R of T is in gallons per hour, if I integrate that over time, I'm going to end up with gallons. So I'm finding a displacement of gallons. You typically in life don't think of it as like displacement of gallons, but that's really what it is. All right, I think we have hit this concept pretty well. Let's take a look at the next one. All right, area between curves. And also my screen time notification just came up, and I am up 7% this week. All right, that's great. All right, so area between curves, I think is a huge deal, but it's like not as huge a deal as maybe I think it is. There was like a 50-year period where one of the first questions on the AP exam was always, the free response question was always area and volume, 100%. So if you want to find area and volume free response questions, they are out there, and I've done lots of them. So just search for the videos and you will see them. All right, here's the scenario. We have a function f of x, a function g of x, and we're going from a to b. So here's the region that we're trying to find, and we want to find the area of that. So the area of this region. So when we're working with x, we're typically going top minus bottom. You're always doing top take away bottom. So it's the integral from a to b of f of x, the top curve, minus g of x, the bottom curve, dx. One way of thinking of that is you're just finding, like, pretend g of x didn't exist. You're finding the area bounded by f of x. Pretend f of x didn't exist. You're finding the area bounded by g of x, and then you're just doing the big area minus the little area. That's really what this comes down to. So that's what we have there. And all of these, so I want to stress this, all of these are x values. This is the key to setting up an integral in terms of y. People struggle with that more than they do with x's. Everything here is an x value. A is an x value. B is an x value. The functions are functions of x. And then we have dx, which is kind of what's setting it all off, the dx that we have there. Now, when, I don't actually know the next thing is going to pop up here. There we go. Okay, so it's the integral from left to right of top take away bottom. That's what you're doing if you're dealing with dx. Integral from left to right. You just read from left to right, so that one makes sense. And then it's top take away bottom, bigger thing minus smaller thing. All right. Now, you also have to deal with these in terms of y, which is not a struggle, but people want to make it a struggle. Here's our graph. Here's our region. Just kind of like fill it in. Now, what you want to do is calm down when you're integrating with respect to y. People freak out. The area here is going to be the integral from a to b, which is bottom to top, and then f of y minus g of y, which is the right curve minus the left curve, right? So you want to do integral from bottom to top of right take away left. If you think about it, when you do the right curve minus the left curve, you get a positive value. Like, think about the x coordinates of f of y. Think about the x coordinates of g of y. If you subtract those, you get a positive value. That's all we're trying to do, is get positives. So this case, every single thing is a y value. So a is a y value, b is a y value. They're functions of y, and then dy is what's setting it all off. So make sure when you're done writing an integral for area that everything has the correct value, variable, I guess, is what I'm trying to say. It's when I said area, I started thinking of volume, and then I was like, like that's a thing. All right, so what is this? This is the integral from bottom to top of right take away left, dy. So a couple of things here. The bottom curve or the left curve, so the x and y axes are frequently involved here, almost always, to be honest. But I guess that wouldn't be area between curves. That would just be area. But anyway, often the bottom curve on the left-hand figure will actually be the x-axis. So you could write minus 0 if you want, but you don't need to. And then on the right-hand picture here, often the left curve will be the y-axis. So you will see that happen from time to time, or maybe often. Other things, when you're dealing with dy integrals, they're often given still as like y equals x squared. So you're going to have to say x equals the square root of y. You have to solve the function for x to get a function of y. So x equals some function of y. That's a really common thing to do, and I think that's the thing that screws people up the most. And then the other thing is, make sure you use parentheses around the functions, right? So like the quantity f of x minus the quantity g of x. In particular, minus the quantity. Make sure you put parentheses around like g of whatever in my two things there. So the bottom function or the left function. If you don't put parentheses there, you're going to screw up distributing that negative sign, and then you will get the wrong answer. All right, let's see. This is going to be like kind of continued. What if the curves just intersect? So what if instead of having arbitrary vertical lines that are cutting it off, or arbitrary horizontal lines cutting it off, what do we do then? We do exactly the same thing. So here's my picture for f of x and g of x where they intersect. So I made the points AC and BD. All right, so the integral from a to b, which are x values, top take away bottom, and then dx. And that's all it is. These are, I actually think of these as being like more intuitive because it's like there's a definite closed region there, but you're still just doing integral from left to right of top take away bottom. And then you could also just have a curve situation that looks like this, right? So here, what we're going to want to do is the integral. So because of the way I labeled these points, kind of strangely, it's like AC is the top point and BD is the bottom point, we have to do the integral from D to C, right? The bottom y value to the top y value of the right-hand curve minus the left-hand curve. So that's all we're doing. I mean, you just set it up, you do it. Do not let the integrals with respect to y scare you. Every year my students just freak out about that. They're not any harder. It's just that, like, you're not used to reading from bottom to top and right to left. Like, you don't do it normally, but it's exactly the same thing. You're just doing right minus left, and you're integrating from bottom to top. So in this case, D to C, because D is the lowest y value, C is the top y value. The right curve is f of y, the left curve is g of y. And there you go. All right, what do the problems look like? Enough of that talking. What is the area of the region in the first quadrant bounded by the graph of this thing and the line x equals 2? All right, so step 1, sketch the region. Doesn't need to look good, just needs to be somewhat accurate as far as left and right and top and bottom go. That's all it needs to be accurate. So in this case, I'm going to integrate from 0 to 2, and then the top curve is e to the x over 2, the bottom curve is 0, and then dx. All right, another problem showed up magically. We want to do, let R be the region in the first quadrant bounded by the x-axis and the graphs of y equals the natural log of x and y equals 5 minus x, as shown in the figure above or whatever. Find the area of R. All right, so you can actually do this in terms of x if you want to. I think the classier way is to do this in terms of y, because to do it in terms of x, you need 2 integrals, which will be like natural log of x from 1 to something, and then 5 minus x from something to 5, I guess. So that would be 2 integrals. It'll give the answer, and that's totally fine. But what I'm going to do instead, I'm going to do the thing, right? It's y equals natural log of x, so that means that x is e to the y, and then y equals 5 minus x means x is 5 minus y. The intersection point, you just need a calculator. Can't solve it without. So I use a calculator on this. I don't have screenshots of that, but hopefully you better know how to use a calculator. Intersections, graphing curves, bounded areas, all those sorts of things. Make sure you definitely go in knowing how to do it, so you're not wasting time thinking like, how am I going to do this on my calculator? No, you want that to be automatic. All right, so this is going to be the integral from bottom to top. The bottom y value is 0, the top is 1.307, and then right take away left. Just calm down and do it. So often when an integral will require when an area, let's say, will require 2 integrals when you're working in terms of x, often you can do it with only 1 integral in terms of y. That's a really good time that you want to do it. And the other thing is, notice these parentheses, that's for safety. If I had done e to the y minus the quantity 5 minus y, those parentheses would be crucial, because if I didn't have parentheses, I would have been doing minus 5 minus y, but I really want to do minus 5 plus y. Also, the next question just like talks about this, so I don't know why I'm bothering. Here's the question. What's the area of the region enclosed by the graphs of y equals e to the x minus 2 and sine of x and x equals 0? I put in an extra and there. This was a calculator question. All of these are pulled from AP exams. You have to know how to do this stuff. But I use a calculator, so I graphed it. Now, what I did here was I graphed the 2 functions. I found their intersection, and then I used the bounded area built-in capability to get the answer. So make sure you know how to do all those things. I have a separate video about that if you need it. But we're going to go from left to right, which is 0 to 1.054, and then top take away bottom. So the top curve is sine, the bottom curve is the quantity e to the x minus 2. Those parentheses are crucial. If you don't have them, you will definitely get the problem wrong. So watch out for that. And it'll be one of the multiple choice options because they know that you do it. So that's like even worse. So our answer here is 0.744798, 3 decimals, 0.745. Make sure you know how to use your calculator. It's going to save you a ton of time mostly. All right. What is the next thing that's in this section? It's still related to this basically. So this would be curves that intersect more than once. That's kind of interesting, right? It's its own section. So let's see what this looks like. We're just going to do what we've been doing, but top and bottom will like switch halfway through. So you just have to be on the lookout for that. I have never seen one on the exam that involved left and right, but there's no reason that it couldn't show up on the exam. But I'm just going to show you this with respect to x. So here we go. We have x1, y1 is the first intersection, x2, y2 is the second intersection, x3, y3 is the third intersection. I do think it's really helpful because I am able to use multiple colors on these. It's really easy to keep track of what's what. So like in a calculus class, I kind of recommend that. I don't think on the AP exam you're allowed to have like, I don't know, if you can have colored pencils, I guess you could use them. Check the rules for that. I don't think it's in the rules that you can do that. But we have two regions, and we're just going to find the area of both of them. So here's our first region, and here's our second region. And you can see in the first region, the green curve is on top, and the blue is on the bottom. In the second region, blue is on the top, and green is on the bottom. So we got to make sure we get that right. Otherwise, and maybe you've run into this before, if you screw up the top and the bottom curve, but you get the bounds correct, what you end up getting is just the negative of the correct answer. So if the correct answer was supposed to be 12, but you screw up top and bottom, you will get negative 12. So like you can fix that if you're aware of it, but when you're adding up multiple regions, you may not even notice, right? You might do the first area is 100, the second one should be 12, but you get negative 12. So your calculator will just spit out 88, and you'll be like, okay, 88, when really you should have gotten 100 plus 12, 112. I think I'm keeping track of those in my head, but who knows? All right, so let's write them down. First one, we're going from x1 to x2, top curve minus bottom curve. Then we're going to add to that the second one, which is going to be from x2 to x3, top curve is now f of x, bottom curve is now g of x. This is not really a big deal. Now, one thing that you should know is it is possible to find this in one shot without caring very much, but not as a human, just as a computer or a calculator, where what you can actually do is you can go from x1 to x3, the absolute value of f of x minus g of x. Now, the absolute value takes care of the fact that sometimes f of x minus g of x is positive, sometimes it's negative. The issue here, well, this could show up on multiple choice. It'll be like, which of the following does give the area of the region? And that could be an option. Sometimes it's one of those like, option 1 would be the first thing I wrote, option 2 is the second thing, and option 3 is some ridiculous thing, and you have to choose like 1, 2, 1, 2, 3, whatever. On your calculator, sometimes the calculator can't really handle this. It depends on your calculator and how complicated things are. So make sure you understand both concepts. I just made one up because it's really hard to search through AP exams to find this type of problem because I have to like read every problem and see it and whatever. So I just made one up, came up with some functions, put them in. The calculator has the bounded area command. The bounded area command will get these right most of the time. I personally do not trust it. I use it to get a sense of the answer, and then I also always do it on like an actual calculator page. But I did this. I got 6.55882. Then I did it again. So this was menu 6.8 on the graph page is bounded area. I did it again on the calculator page. The one method where I just like added everything up, and I got 6.55882. And then I also did the integral of the absolute value thing. That's like warning me of something. I don't know. The warning sign just makes me nervous. So I would still do it. But, and sometimes you can't do anything about a warning sign. But nobody wants to see a warning sign in the middle of the AP exam. So make sure you know all three of those methods so they're available to you. Also, if your calculator just starts spinning forever, it's not calculating, hold down the escape button. If you hold that down long enough, it will stop calculating what you're calculating. Then you got to find another way to approach the problem, but at least you can go back to using your calculator, which is a huge deal. All right, moving on. 8.7 and 8.8, because I think the way they separate these things is weird. Maybe. Oh, I'm boxing the answers. I was like, why is it not going? All right, here goes. Volumes with cross sections. Now, what cross sections are we responsible for? We are responsible for squares, rectangles, triangles, semicircles. But I think I could make the case, and I think they would make the case, that basically everything can be treated as a rectangle. And so, like, these are the definite shapes, but sometimes they kind of go a little rogue on this. And we'll try to look at that as well in some example problems. All right, so what does the volume look like when you were dealing with this? So actually, that's not the right question. Well, that is what I want to talk about, but like the actual thing you see with your eyes, the shape that you get is like 3D printed objects. Search the internet for those. You'll find a lot of examples. The really nice thing is you do not need to be able to picture them to be able to find their volume, which is great because I can basically never picture them. The volume is going to be the integral from a to b of a of x dx, or the integral from, I'm calling it c to d of a of y dy. Now what's a in this case? A is just the area of a cross section, right? The area of a square is side squared. The area of a rectangle is base times height. Triangle, 1/2 base times height. Semicircle, a little more complicated. We're going to get there. But that's all we're doing. If you can find the area of the cross section and integrate it from where you start to where you stop, you're good. Let's look at a picture. All right, so I have the point AC is the bottom point, BD is the top point. The left function I'm calling f of x or k of y, because you could write that as a function of x or y. The right or bottom function I'm calling g of x, it's getting confusing as I talk, g of x or h of y, because again, you could do that either way. All right, now we need to know if our cross section is perpendicular to the x-axis, which is the most normal thing, or to the y-axis. Let's deal with the x-axis first. So here's our cross section. I always label it S. I label it S for segment, but I will then refer to it as side like all the time. But S is the segment that we're dealing with, and then somehow the shape is related to that segment. So if S is perpendicular to the x-axis, then it's just like with area, we're going to be doing top, takeaway, bottom. Top, takeaway, bottom with respect to x is like the thing. If S is perpendicular, okay, I guess I'm writing top and bottom. There you go. I write this out ahead of time. It takes like hours, and then I talk over it, which also sometimes takes hours. Hard to remember all the things I did as I'm going. All right, so what if S is perpendicular to the y-axis? So what you're doing when you do these problems is you're going to draw S. Draw in that segment so that you lock in what you have to really think about. So if S is perpendicular to the y-axis, it's like the weirder situation. So I always think everything with respect to y is like a little bit weirder, requires a little bit more thought, right? With respect to x is default mode. X goes from left to right, top and bottom. All the functions are x values, and then it's with respect to x. So if you're dealing with perpendicular to the y-axis, S is going to be h of y minus k of y, which is just right take away left. As we know, that comes up all the time. And everything's going to be y, so bottom y value to top y value, functions of y, dy, everything will be y. With respect to x is the normal one. That's like how my brain thinks about it. With respect to x is the normal one, so with respect to y, everything is weird, and it's easier to remember that way. So what are the areas? I'm going to write them all in terms of S, right? So S is either top takeaway bottom or right takeaway left. Squares. Squares are just S squared, right? We know that. Rectangles. Rectangles are a little weird. They're going to be base times height. It's just going to be like described to you. So it's usually going to be like S times some number times S, which works out to that number times S squared. So you'll be told like the height is 5 times the base, and the base is in the XY plane or something like that. They have to describe that. Or sometimes, a little bit weird, this is like the random description. They'll tell you that it's a rectangle with the base is S, and then the height is just like 7x squared. And there's nothing you can do about that. You just do base times height. The height is 7x squared. Like, good. And you just got to do the problem. All right, triangles, you got to just go with the description, right? So it's 1/2 base times height. But like what kind of triangle is it? Is it an equilateral right triangle? Is it an isosceles triangle? Is there such a thing as an equilateral right triangle? There is not. Is it an equilateral triangle? Is it an isosceles right triangle? Like, read the description. So they will describe it to you. You just have to work out how to do 1/2 base times height. What's the base? What's the height? Semicircles. 100% is the one that you must memorize. I'm not going to go through why this is true here, but I have videos on it, and it's in the notes of it's in the videos of me doing the notes also. It's pi over 8 S squared. That is how you find the area of the semicircular region. This one is must memorize. You do not want to have to work that out on the AP exam. All right, so that's like the basic idea. I want to add the caveat. We're always just integrating area of a cross section. If you don't know or understand the volume that they're describing to you, take it from me, it is a rectangular prism. You can think of almost everything as a rectangular prism if you make things small enough. And because of that, you can always like draw a rectangular prism and then kind of label it up. So you got like your delta x, you got maybe that's s, right? That's in the xy plane. And then the height is just going to be like something they tell you, h of x. If you do this, the volume of that is just the product of those three things, and then you integrate it. So this, I'm aware, is not the best description. We're going to see one problem where we actually have to do something like this. But if you are confused about what they're describing, they are describing a rectangular prism. Draw the rectangular prism and label things, and then just multiply and integrate. All right, what do some problems look like? R is the region in the first quadrant bounded by y equals x squared, bounded below by the graph of y equals x squared, above by the graph of, so below means it's the floor, and above means it's the ceiling. I have students who screw that up every year, and it blows my mind. Just think it through, and you will work out what is above and what's below. Also, when you graph this, you can't like really get it wrong, but R is the base of a solid whose cross-section is perpendicular to the x-axis. That is very relevant to us. Are squares. All right, perpendicular to the x-axis and are squares. So step one, draw this thing and put in the segment, right? Perpendicular to the x-axis. So in this case, I want to do the integral from 0 to 1, those are x values, of top take away bottom, and then I want to square it because the area of a square is side squared, or s squared. S is top take away bottom, root x minus x squared, s squared dx. I said that like a million times, but that's it. All right, and that's it, right? And this is probably a calculator question, but not necessarily. Sometimes they make you do a problem like that, and it's super annoying. All right, let's take a look at the next one. The region enclosed by the graphs of y equals x squared and y equals 2x is the base of a solid. For the solid, cross-section is perpendicular to the y-axis, so we're going to have to draw that in, is a rectangle whose height is 3 times the base. This is what I was talking about. They're just going to describe it, and you just go with it. So which of the following expressions gives the volume? We don't have the options, but let's draw. So here's our region, perpendicular to the y-axis. If you're perpendicular to the y-axis, everything is weird, right? So everything is weird, so I don't have y equals f of x. I need to have x equals a function of y. So I need to convert each of these. So I'm going to say this is x equals root y, and this is x equals y over 2. So I took both equations and I solved them for x. That's a step you need to remember to do. Now, what is the area of this thing? Well, it's a rectangle, so it's going to be base times height. The base is just going to be right take away left. So right take away left is the base, and then the height is just 3 times the base. So times 3 times the base, which is right take away left. So we get this. So in this case, we've ended up with 3 times s squared. And, you just read the description and see what to do. So we're going to go 0 to 2. This 2, by the way, is the y value. I hate the way they always use regions that have like a intersection along the line y equals x, so you can never really tell, like, is it the x value or the y value? That is a y value because it's dy. Everything must be y. Now, what is our area? It is 3, the quantity s squared. So this, and then dy. That's our answer. And then we would choose it, presumably. I'm going to look at a bunch more of these, because these are a big deal. Volume stuff is kind of like the big deal. So here goes. Let R be the region in the first quadrant bounded by the graphs of 4 cosine pi x over 4 and y equals the quantity x minus 2 squared. The region R is the base of a solid, perpendicular to the x-axis, isosceles right triangle with a leg in the region. So perpendicular to the x-axis, isosceles right triangle, leg in the region. Perpendicular to the x-axis. Draw that in and you will screw it up less often. Now, a good hint or tip or whatever, it's a tip, not a hint, for the AP exam is name your functions and then use the names. So what I'm going to do is, like, on my free response, I'm going to say let f of x is going to be my cosine thing. I'm not going to make you watch this. And then g of x is going to be my quadratic. And now I can just refer to f of x and g of x, and I'm less likely to make a copy error, like copy down the function wrong. And I think that's a really good hint or tip. Why do I keep saying that? All right, so what am I doing? Here's f of x. Here's g of x. We need the actual volume, so this is almost certainly a calculator problem. I don't remember offhand, but I think it probably is. All right, so I need to figure out what an isosceles right triangle is. So just sketch it. When you don't know what you're doing, start sketching figures. That's like, in math, that's kind of like words to live by. When you get lost, sketch a picture of the scenario. So this is my isosceles right triangle. A leg is in the region, so one of the legs of this thing is S. And then the other one is also S because it's isosceles. So now I know the area. It's 1/2 base times height. It's 1/2 S squared. And now I can work with that. So my volume is going to be the integral from where I start to stop, so 0 to 2, of the area, which is 1/2 S is top take away bottom squared. 1/2 S squared. And just integrate it from 0 to 2. That's what we get, and then I would use a calculator. I didn't bother to find some of the numerical values in this. All right, let's take a look at another one. Let R be the region bound. Why is that so big? Let R be the region bounded by the graphs of sine of pi x and y equals x cubed minus 4x. The region R model. This is what I was talking about. The region R models the surface of a small pond. Okay, that's not a shape I'm familiar with. At all points in R, at a distance of x from the y-axis, the depth of the water is given by h of x equals 3 minus x. Find the volume of the water. Okay, so a distance of x from the y-axis means I'm basically perpendicular to the x-axis. So I'm going to draw that in. So that's a thing. Now, what am I dealing with? I don't really know. So what I'm going to do is draw a rectangular prism and see how things kind of like work out. So the depth is 3 minus x. All right, so I'm going to try to label this up a little bit. So I don't know if you can tell the difference between the green and yellow things there. The yellow ones are S, that's in the XY plane. And then the green things are H, that's my H of x. So S, using my own tip, I am naming the functions because I did not want to handwrite those like ever. So f of x is sine of pi x, g of x is x cubed minus 4x. On the real exam, I would write a nice thing like let f of x equal and g of x equal and go from there, but this isn't the actual exam. All right, label this up. So that right there is S. That's f of x minus g of x. Now, what else? This little segment here is like a section of the x-axis, so I'm going to call it dx. Like I'm slicing up the x-axis. That's my dx. And then this height here is h of x. So the volume of this slab that I've drawn, this rectangular prism, would be the quantity f of x minus g of x times h of x times dx. That's my rectangular prism. Now I just integrate it over the interval, which is from not divide by, just the bounds are 0 to 2. So I'm going to integrate from 0 to 2. And then the product. So f of x minus g of x times h of x, and then dx. So if you get lost, it's a rectangular prism. That's like hard to work out at first, but it's true. All right, next up, let's dive into some more volume stuff. So instead of known cross sections, which might be my favorite to do because they're like so straightforward, just find the area of a cross section and integrate it. We're going to do volumes of revolution, which you might know as disks and washers. I rarely use that because I just think we're finding volumes. Everything that we do with disks and washers or volumes of revolution based on the area of a circle, which is pi r squared. So you're going to see pi and then r squared a lot. And it's based on the volume of a cylinder, pi r squared h, which is really in calculus terms, pi r squared dx or dy if you're going around the y-axis. All right, so what do these look like? The next couple of slides are like me developing this concept. If you're like locked in on this, you could skip ahead a bit, but I'm going to do it. I'm going to come up with like everything, and I think it's going to take a while. Here's our picture. We're going to go, so when you're rotating, show a little arrow of what you're rotating around. So we're going around the x-axis. So show a segment for the big radius that you're going to get, right? So as you go around, f of x is creating an outer edge. The radius of this shape always goes from the x-axis out to f of x. The radius, r, is just f of x in this case. So for every x between a and b, you calculate f of x, rotate it. You get a circle, and then you like add them up. So the volume is going to be pi times the integral from a to b of the radius f of x squared, pi r squared, and then dx. That's all we're really doing. All right, now in terms of y, everything is basically exactly the same, right? You're going around the y-axis, so you put a little arrow. I'd like to stress that. Put the arrow so that when you go back to your work, you're like, what was I even doing, right? You'll see it. draw something there, your radius, perpendicular to the axis you're revolving around. So our radius is f of y, and our volume, again, is just pi r squared integrate. So it's going to be pi, the integral from a to b, those are y values because you're going around the y-axis, which is vertical. It's not normal. Everything has to be weird. Everything has to be a y value in this case. So we just get pi, the radius squared, integrated from a to b. So in general here, what we're really doing, little things to do. Sketch the region, definitely. Show the arrow, and then draw a segment for r. Do that every time. Get used to it. Make it like muscle memory. You'll dominate these. I actually like these problems because they're usually just set up but do not evaluate, which is my favorite thing on the exam. Don't forget the pi, especially on a calculator problem. People will set it up correctly and then forget to type in pi, but just in general, always be thinking volume, pi r squared. Gotta have pi in there. If it's volume of revolution. Volumes with cross-sections don't all have pi, as we previously saw. And then this is like the general method, right? We get pi, the integral from a to b of r squared dx, or pi, the integral from a to b r squared dy, where if it's dx, everything's x's, dy, everything is y. That's the idea. Now, what if it's more confusing? What if there are two curves? This is what you would commonly refer to as washers. I just think in the real world, people don't think about discs and washers that much anymore. Like a disc is like a frisbee, and a washer is like, what is a washer like in your world? If you know nuts, bolts, and washers, it's like that. But like an old school CD or a DVD or a Blu-ray, like those are washers basically. They have a hole in them. They're like a disc with a hole in it. All right. So this is our picture. Another function has entered the arena, right? So instead of just f of x, we now have f of x and g of x. Well, that just means we get two radii. So we're going around the x-axis. Here's our big radius, right? You start at the axis and you go until you hit the farthest out curve. That's your big radius. Then you start at the axis and you go until you hit the innermost curve. That's your smaller radius. So your big radius in this case is just f of x, and your small radius is just g of x. So really what we're doing in this case is we're just doing the big volume minus the small volume. So what that's going to end up looking like is pi times the integral from a to b, and those are x values. The big radius squared, so in this case it's f of x squared, and then minus the little radius squared. So we're doing big volume minus little volume. You could actually do them as two separate integrals, but most people combine them into one. But if you don't like that, do it as two separate ones and you will never get it wrong, and that would probably be good. So we're just doing pi, the integral from a to b, big radius squared minus little radius squared, and then dx, so everything is an x value. Of course we could do this with respect to y. So we have f of y is the rightmost curve, g of y is the leftmost curve. We're going to go around the y-axis. So we're going to draw our radii perpendicular to the y-axis. Big radius. So with y, you're always doing right take away left, right? With x, you're always doing top take away bottom. Here we're going to do right take away left. So f of y minus 0, basically. And then we'll have a small radius, which is going to be g of y minus 0, or just g of y. So our big radius, the yellow one, is f of y. That's really f of y minus 0. And our little radius is g of y, which is really g of y minus 0. Because remember, the y-axis is x equals 0. So you're doing x equals g of y minus x equals 0. So g of y minus 0. Now the volume looks exactly the same, except it's dy, so it's all weird. Everything has to be y values, including the bounds. Don't forget that. Just say it to yourself a lot, like, oh, it's dy, everything is weird. Or it's around the y-axis, everything is weird. As soon as you say that, it like triggers like, oh, everything needs to be in terms of y, which I've decided is the weird thing. And then we get pi, the integral from a to b of capital R squared minus lowercase r squared, or big R squared minus little r squared dy. You're really just doing big volume minus little volume. That's like all you're really doing when you do these problems. Keep that in mind, and it will, make your life a lot easier. All right, now there's another section, and then we're going to do problems. So, like, again, if you have this locked in, you should have skipped a lot, and maybe I'll try to put a timestamp back when, so this conversation, hopefully it doesn't mean anything to anyone. All right, what if we were going around other axes, so not the x-axis or the y-axis, but like a generic line? Well, here's our picture. We're going around this generic line. This is y equals something, right? So that means that our radius is going to go from the axis to the curve. That's all you need to do. Draw the picture correctly and then figure out the correct thing for r, right? So this is y equals our axis. So our radius r, in this case, is, because it's with respect to x, top take away bottom, right? So we're doing top minus bottom. So axis minus f of x, that's r, and then you're always just integrating. You're doing pi r squared, right? So we're going to get pi, the integral from a to b, r, which is axis minus f of x, top take away bottom, and then squared dx. That's all there is to it. It's not a big deal. We're just shifting a little bit. So we could have this, right? Where that axis was above the curve. This axis is below the curve. We're still going around a horizontal axis. We draw our segment perpendicular to the axis. Now this time, r is going to be top take away bottom. Actually, it's always top take away bottom. It's just a question of what's top and what's bottom. F of x minus the axis. And we're doing pi, the integral from a to b, of r squared, pi r squared. You're always integrating pi r squared. And we get that, that's dx. Everything is x values. Could we do, so I mean, this is the general rule. For r, we're going to draw a segment between the axis and the curve, then do top take away bottom. What if there are two curves? So I am going a little quickly through this, but it's because like we're belaboring a point and hopefully you kind of know what you're doing. If you don't, I have other videos where I do all of this in extreme depth, unfortunately. Not unfortunately, I mean, it's unfortunate for me because I just keep making the same videos, but what if we have two curves? Well, if you have two curves, you have two radii. Draw them in, do the problem. You're still just doing big volume minus little volume. So we're going around this. We have a big radius. We have a little radius. There you go. So our big radius is the axis minus f of x. Our little radius is the axis minus g of x. It's really helpful if you can color code everything. It'll drive you nuts if you try to do it, but it's useful. So the volume is pi, the integral from a to b, the quantity, big R squared minus little r squared dx. Everything is an x value. So that's what you're always doing. Just kind of like calm down about it, set them up, not a problem. They do look ugly while you're like writing them out. As you can see here, I chose to just write big R squared minus little r squared instead of like, that was for space reasons though. All right, and then what if the axis is below the region? Same deal. We're going around this. Draw big R, draw little r, write them down. Top take away bottom. When you're dealing with dx, the kind of normal thing, it's always going to be top take away bottom. You're always doing top take away bottom. So if you draw the picture, big R is bigger than little r. It's not confusing. To get the big volume, use big R. To get the little volume, use little r. And our volume will again be this. It looks identical. And we are really just doing big volume minus little volume. All right. Oh, gosh. All right. What if it's vertical? What if it's vertical? This one, I started to get tired of even writing them, so I'm going to just blast through this. The big idea is vertical axis, dy, everything is weird. Also, you have to use right takeaway left. So instead of doing top takeaway bottom, you're always doing right takeaway left, which just gives you positive numbers. So we could have this. In this case, I drew it. I drew r. Right takeaway left is f of y minus the axis. Our volume is pi, the integral from a to b, r squared dy. dy, everything is weird. Everything must be a y value, including the bounds. All right, the axis could be on the other side, in which case you will get this. And if you want to look at that, pause it and look at it. You could have two curves. Now you just have two radii. So you have a big R, you have a little r. It's right takeaway left for both of them, and one of them is bigger than the other. So you're doing big volume minus little volume. Try to think of it that way. So we get pi, the integral from a to b, big R squared minus little r squared. And then the axis could be on the other side. Oh look, I forgot to put the arrow in. I'm not gonna fix that, but that's my eternal shame. I forgot to put the arrow. We're revolving around that axis. Should be there. That's -1 for this video. All right, and we get that. Now, let's do some problems. Let's do a bunch of problems. So hopefully, this is where you're jumping back in if you thought you understood everything about volume, and that's great if you did. What is the volume of the solid generated by the region bounded by x equals root y minus 2, and the lines x equals 0 and 5 and y equals 5. There's so many things about the y-axis. I don't even know what I just read. I'm going to draw the region. So I need to figure out how to graph x equals root y minus 2. What I usually do is just solve it for y. I know that's like an extra step, but again, I'm not really sure what that looks like. So I solve for y, and I do know what x squared plus 2 looks like. So we're going to do this. All right, so we get this. And that is the curve x equals root y minus 2. So what are we doing? We're going around the y-axis. There's our arrow. Perpendicular to the axis is r. Right take away left. So root y minus 2 minus 0. It's just root y minus 2. So we are going to do pi, the integral from, I'm going to change that to that pink color that I've been using for lower bounds, 2 to 5, r, which is root y minus 2, squared dy. There you go. You could definitely do that by hand. I don't know what this was on the exam. All right, find the volume of the solid generated when r is revolved about the line y equals negative 3. All right, so in this case, y equals negative 3 doesn't like fit easily, and also the functions aren't named. So I'm going to sketch in the line, just like put it below it. It's got to be below. So definitely like draw the axis, because then you can draw in your r values. And also, I'm just going to name the functions and color code them. For convenience in the video, and in the real world, it's also very convenient if you can get away with it. So we need this intersection point. So 0.765 and 0.552, definitely a calculator question. You can't find those by hand. And then another thing I'm going to do to make my life easier is I'm going to say let A equal 0.764972. So now everything I write, you can do this on the exam. I can use that instead of handwriting 0.765 over and over again. I'm just going to use A as my bound. So I need big R. And in this case, because the region is called R, I'm going to use a subscript and call it R sub 1. And then I'm going to do the same thing basically for little r, but it's top take away bottom, so f of x minus negative 3. Which just think it's always top takeaway bottom if you're doing dx. And then this will be top takeaway bottom. So R2 is going to be sine of x squared, or I named it g of x minus negative 3. And then I used a calculator for this. I mean, you basically need to use a calculator. So it's pi, the integral from 0 to a, quantity big R squared minus quantity little r squared. Make sure you're putting parentheses around those quantities or there's just no chance. And then this is, why did I write dy? This is dx. That is definitely, that's an error right there. I'm going to actually try to fix that. This is dx, not dy. Come on. So I use a calculator for this. I graphed it. And then after I graphed it, I also just on the calculator page did this. So the actual area that we're getting, volume. The volume that we're getting here is 11.841. And then we would pick that, or this is probably, this is a free response question, so we would not pick it. We would just write it. All right, let's take a look at another one. So a vase or a vase has the shape obtained by revolving the curve y equals 2 plus sine of x from 0 to 5 about the x-axis. So this is where they're like, let's give it a context instead of just like telling you to find the volume. But the problem is, what is the volume? So I'm just going to sketch the region. This one's not bad. Again, that region, all that needs to be accurate in that region is top curve, if there's a bottom curve, right and left. That's all that really matters. The actual shape doesn't matter because like we're not trying to draw the 3D figure. So these are our bounds. There's r. So r is just 2 plus sine of x minus 0, but 2 plus sine of x. So we're just going to do pi times the integral from 0 to 5 of the quantity 2 plus sine of x squared, pi r squared. So when you're dealing with volume, tell yourself pi r squared over and over again. Let's do another one. I got, what do I have? This is actually the last question that if you're in AB, this is the last question that you need to follow along with. You're going to get right at 1 hour, it looks like. All right, R is the region in the first quadrant enclosed by the graphs of g of x, which is root x, and h of x, which is x over 3, as shown in the figure. Right, but do not evaluate, the best thing. That is the best thing you can see on the AP exam. An expression involving one or more integrals that gives the volume of the solid. R is revolved about the horizontal line y equals 4. I don't know why you would think you would need more than one, but whatever. So we dot it in. That's at y equals 4. We have a big radius, which I'm using a subscript for because they name the region R, which is so annoying. And then that's going to be top take away bottom. So 4 minus, what is the bottom curve? It's x over 3. It's this blue curve here. So h of x. And then we'll have a little r, which we'll call r sub 2. And that's going to be top take away bottom. So 4 minus g of x, because it's the only thing left. G of x is this green curve. It's radical x. But again, if a curve is named, use the name. Don't write it out. You're more prone to make mistakes if you try to write out like the algebraic expression. So the volume here is going to be pi times the integral from 0 to 9 of big R squared minus little r squared. And that's it. That's volume. That actually, if you were in Calc AB, that is all of Unit 8. You made it. We reviewed all of it. If you're in BC, we're going to do one more thing because you have to do something else. So if you're in AB, again, as always, I hope this was helpful and good luck. If you're in BC, follow along. One more. All right, arc length of a function. Arc length of a function could totally be a Calc AB topic because there's nothing in it that's not AB type material. Here we go. Arc length of a function is the integral from a to b square root of 1 plus f prime squared. So you got to find the derivative and then square the derivative. So usually you just have to set these up. The reason being, it's unusual to be able to integrate the square root of 1 plus something squared, right? Like, how often do you find yourself doing that? And then another thing is, I couldn't find an example, but it's actually a common multiple choice question to figure out what f of x is given the actual arc length integral. So you'll be given arc length, and then you have to rearrange arc length so it looks like square root of 1 plus something, and then you have to recognize that that something is f prime, and then you just integrate it. So that's another thing. A third thing to think about with this is arc length will come up a lot when you're dealing with parametric equations and vector functions, but that's not in this unit, so I'm not doing those problems, but that's actually, I would say, the more common place that you see it. But for functions, let's look at types of things. So which of the following integrals gives the length of the curve? Y equals natural log of x from 1 to 2. I mean, this is the type of problem you'll be asked. You just have to know how to find arc length. F prime is 1 over x. So plug in. We're going from 1 to 2, and then square root of 1 plus 1 over x squared dx. There you go. Let's take a look at another one. I just like this problem, so I threw it in. Like, I saw it, and I was like, oh, no. And then I was like, no, we should do this. Table above or below gives selected values for a differentiable function f and its first derivative. Use a left Riemann sum with 3 subintervals of equal length. Which of the following is an approximation of the length of the graph of f from 1 to 7? All right, this is a really good question. So step 1 is just write down arc length, right? So 1 to 7, 1 plus f prime squared dx. All right, now the issue is like, what do we do with this? Well, when you are confused about the integrand and you have to do a Riemann sum, rename the integrand. So what I'm going to do is I'm going to say, let g of x equal radical 1 plus f prime squared. So why is that advantageous? Well, I can actually find values of g of x now, right? I have to do f prime squared. So take at x equals 1. F prime is 2. Square it. You get 4. Square root, add 1, 5. Square root it. So root 5. And then just keep going, right? So at 3, it's 1 plus 1 is 2. Square root it. At 5, it's 1 plus 0 squared is 1. Square root it. At 7, 1 plus the quantity negative 1 squared is 2, square root it. So now we know the values of g of x. Now we're just doing a left Riemann sum for the integral from 1 to 7 of g of x. When the integrand is confusing, rename it and it will be less confusing. And that's how you can turn basically everything into a rectangle. You might recall for the volumes by cross sections, I said basically everything is a rectangular prism. Same thing here. Everything's a rectangle if you look at it in a certain way. So this is just going to be a left sum. So from 1 to 3 is 2, and then the left is root 5, and then from 3 to 5 is 2. I mean, they said they're equal size, but whatever. And then the left is root 2. And then from 5 to 7 is 2, and the left is 1. And there we go. That is all of Unit 8 of AP Calculus. You'll see this in Calc 1, the end of Calc 1, the beginning of Calc 2 if you're in college. It's a lot of stuff, but I hope you found this helpful, and good luck.